Okay everyone, this is discussion 3.3, spectroscopic identification of organic compounds. And this says practice makes perfect because this is not a topic that you will be able to learn just by studying your notes. You're going to have to do things. You're going to have to practice this to get good at it. Okay, so we're going to give you lots of opportunities for that, but when you're studying, make sure you go back and do practice problems. That's the way to get good at this. Okay, the first thing we're going to talk about is the index of hydrogen deficiency, or the IHD, and this tells us about the degree of unsaturation that a compound has. Now, you probably recall that a saturated hydrocarbon has no double bonds or triple bonds, and an unsaturated hydrocarbon could have double bonds, triple bonds, or ring structures. Okay, a double bond is 1 degree of unsaturation, a triple bond is 2. A ring is 1, and an aromatic ring with alternating double bonds, like a benzene ring, is 4. Now we can work out the IHD from the structure, or if we're given the formula, we can figure out the degree of unsaturation, so the number of double bonds, triple bonds, rings, etc. That can sometimes be a little bit more helpful because if we're trying to figure out the structure of a compound, it would be nice to know in the end what the IHD is going to be. Okay, so if we calculate IHD from the structure, it's pretty straightforward. We just have to look and count up the number of multiple bonds or rings. So benzene, for example, has 1 ring and 3 double bonds. So the total number of rings and multiple bonds is 4, so the IHD would also be 4. Cyclobutane, just 1 ring, so 1 and 1. Same with cyclohexane. Cyclopentadiene has 1 ring and 2 double bonds, and then aspirin presents a really nice challenge because you have to use the skeletal structure to figure out you don't have to use the skeletal structure to figure out the IHD, but then you can figure out the formula and double check your work, which is kind of a nice challenge using the skeletal structure. Okay, so this is pretty straightforward. It's really just counting at this point. Going back the other way is a little more challenging. So when you calculate IHD from the formula, you have what looks to be kind of a long and cumbersome formula, but it's really pretty simple. The IHD is 0.5 times 2 times the number of carbon atoms plus 2 minus the number of hydrogens minus X, which is the number of halogens, plus N, which is the number of nitrogen atoms, where the following is true. So that just shows you that little c is the number of carbon atoms, etc. Now notice that oxygen does not factor into the IHD. We're addressing that specifically because people really think that it should, but it doesn't. Okay, so if we wanted to calculate the IHD for this compound, we know there are 4 carbons, 0 nitrogens or halogens, 2 oxygens, again, not going to factor into our calculations, but good to know, and 8 hydrogens. So when we calculate the IHD, we would get 1. So if we were trying to draw the structural formula for this compound, we would know that we'd need to have at least, well, not at least, exactly 1 double bond or 1 ring. Now, we're going to use 3 different types of spectral analysis in this topic, and it's really, really useful when we're talking about organic chemistry. Because most organic compounds have a lot of structural isomers, just knowing the formula is not particularly helpful. Okay, but if we use spectroscopy, we can learn things about what functional groups might be present, how atoms are arranged, and we can figure out a lot about the structure of a molecule. So we're going to use 3 different types of spectra: infrared spectroscopy, mass spectrometry, and HNMR spectroscopy. So infrared spectroscopy works on the idea that every bond in a molecule is basically a spring that can be bent or stretched. So based on the mass of the atom, the strength of the bond, the frequency of the vibration will change. And so based on the frequency, we can try to figure out what atoms, functional groups we have. Only polar bonds are going to vibrate and be what we call IR active. So if it's a nonpolar, we're not going to see anything in the IR spectrum. So by examining the spectrum and using the data booklet, table 26, we can get information about the functional groups that might be present in the molecule. Okay, so this is an example. This is the IR spectrum of butanoic acid. So when we're looking at this, there's a lot of noise in this spectrum. We're going to see a ton of little peaks, but what we really want to focus in on are the really strong big peaks. So when I look at this, I see that there are 2 really obvious absorptions. One is near 3,000 wave numbers. And if you look in the data booklet in table 26, you would see, okay, right around there, we expect to see a strong and very broad peak that's caused by the hydrogen bonding of the hydroxyl group within the carboxyl group. We know this is butanoic acid, okay? And that makes sense, right? We know we have a carboxyl group since it's butanoic acid. There's another obvious absorption at 1700 wave numbers. And that's caused by the carbonyl group within the carboxyl group. And again, you can get that by looking at the data booklet. Now, mass spectrometry, we've talked about a little bit in the past. So when we have the ionization step in the mass spec process, we create what are known as molecular ions. And this has the entire mass of the molecule, but it's lost an electron. And this process is so energetic that we do get some molecular ions that are just ionized, but we can also break down those molecular ions into fragments. We can look at the mass to charge ratio, the M to Z, of each fragment, and it'll tell you what that fragment is. So table 28 in the data booklet has some of the most common mass spec fragments. Okay, so let's look at an example of the kind of question that they could ask you using mass spec. So this says the mass spectrum of a compound with empirical formula CH2O has its highest numbered peak at a mass to charge ratio of 90. What is the molecular formula of this compound? So this sort of seems like a mass spec question, but this is really just an empirical formula, molecular formula question. The highest numbered peak is going to be at a mass to charge of 90. Okay, so that means that that's the mass of the molecular formula. Now, when it says the largest peak is the molecular ion peak, I should really clarify that. We mean the highest numbered peak, not largest in terms of height of peak, largest in terms of mass to charge ratio. Okay, so we know that the molecular formula has a mass of 90. CH2O has a mass of 30. So there are three empirical formula units in the molecular formula. So the molecular formula, we multiply all the subscripts by 3 and get C3H6O3. Now, this is where we're going to use that data booklet piece. The spectrum shows a fragment at mass to charge ratio of 29. What piece of the molecule might this represent? Okay, so one thing that's really important to take into account here is we know that if we have a peak at 29, we probably also have a peak at 61, right? Because that molecular ion, when it split, if it gave you a piece at 29, it also gave you a piece at 61. So look for both in the data booklet. Sometimes they're going to give you a peak in the problem that doesn't appear in the data booklet. So when that happens, subtract from the molecular ion peak and look that one up, if that makes sense. If it doesn't, come ask me. Okay, so the data booklet tells us that a peak at 29 could correspond to an ethyl group, CH3CH2, or a carbonyl group with a hydrogen, so presumably from an aldehyde. Both of these are possible fragments given what we know right now, right? Given the formula that we have, both of those are possibilities. Okay. Our last type of spectroscopy is HNMR spectroscopy. NMR stands for nuclear magnetic resonance, and it provides information on the different chemical environments of hydrogen. So hydrogen environments are just saying that the hydrogens are in different chemical environments. Hydrogens attached to the same carbon are in the same environment. So for example, if I have a methyl group with 3 hydrogens attached to the same carbon, those 3 hydrogens are in the same environment. Now, unless they're completely symmetrical or identical, hydrogens attached to different carbons are in different environments. Okay, so the relationship between the number of hydrogen environments in the NMR spectrum is that we will see a peak for each hydrogen environment. So if there are 4 different hydrogen environments, you would expect to see 4 different peaks in the NMR spectrum. Now, the x-axis on the spectrum is known as the chemical shift, and the units are parts per million. This can give us a lot of information about the hydrogen. For example, if it's at the end or the middle of a carbon chain, if it's near a certain functional group, etc. And so those are in table 27. Now, TMS is tetramethylsilane, looks like that. And this is the standard compound, and we base all chemical shifts off this. So this is set as a chemical shift of 0. And we use this because it's easily vaporized, and all of the hydrogen atoms are equivalent to each other. They're all in the exact same environment, so it gives us a nice strong peak. And also, since they're attached to silicon, they're not going to overlap with other things that we're looking at. Now, when we count hydrogen environments, we're going to do a couple examples, and I'm going to let you do some practice. So methanoic acid. Now, the first hydrogen is in one environment, and the second hydrogen is in a different one. They are not attached to the same things. It's not completely symmetrical, so we have 2 different hydrogen environments and 2 peaks. Now, pentane is a little more interesting. If you were doing this quickly, you might look and say, well, there's 5 carbons with hydrogens attached. There's probably 5 environments. Not so. This is a completely symmetrical molecule, so the hydrogens on both ends are in equivalent environments. If I rotated this entire molecule in space 180 degrees, you wouldn't be able to tell the carbons on each end apart from each other. Okay, so because it's completely symmetrical, those end hydrogens are in similar environments. If it was not completely symmetrical, that would not be true. All right, and then the carbons that are one in, their hydrogens are in similar environments, and in the center, that's a different hydrogen environment. So we actually only have 3 hydrogen environments in this molecule, and so 3 peaks. Okay, try these next 2 compounds, and we'll check your answers. Okay. So formaldehyde is completely symmetrical. Those hydrogens are attached to the same carbon, so they're in the same environment. Now in this molecule, it's a little more complicated because you really have to look carefully at that skeletal structure. Those carbons that are circled, remember that all of those do have a hydrogen attached. We don't show it in the skeletal structure, but it is there. So the hydrogen that's attached to that, the hydroxyl group, there is in one environment, and then as they get further away from the hydroxyl, they're in different environments. But they're 2 hydrogens on either end that are in equivalent environments, so we would say those are the same. Okay, try these. So propan 1-ol has 4 different environments and 4 peaks. The hydroxyl group at the end means that the hydrogens attached to every other carbon are in different environments because they're different distances away from the hydroxyl group. It's not a symmetrical molecule. And in 1,3-dichloropent-1-ene, there are 3 environments. The 2 hydrogens on the end that are attached to the same carbon are in the same environment. Now, when you see an NMR spectrum, you're going to be given an integration trace for each peak. This tells us the area under the peak, and that's going to give you the relative ratio of hydrogens in each environment. So if we go back to the previous slide, we can figure out the ratio of the integration traces for each environment. So I color-coded them with the hydrogens. Since there's one hydrogen in the blue environment, the integration trace would be 1. Then it would be 2 in the red environment, 2 in the green, and 3 in the purple. So that would be the ratio of the integration traces. And then for 1,3-dichloropent-1-ene, it would be 1 to 1 to 2. Now this also, the integration trace is going to give you the smallest whole number ratio. So if it's 2 and 3, that could correspond to 4 and 6 carbons. So you have to be a little bit careful about that. Now, we can also zoom in on the peaks and see what are called splitting patterns. So for every hydrogen environment, the splitting tells us how many hydrogens are on the next adjacent atom. If there are no neighboring hydrogens, we're going to see a singlet, so it's not going to be split at all. If there's 1 neighboring hydrogen, we'll see a doublet, so 2 little peaks. 2 neighboring hydrogens, we'll see a triplet. 3 neighboring hydrogens, we'll see a quartet. And you don't really need to know beyond quartet. Okay, so let's look at these hydrogen environments. So the blue hydrogen is a triplet because if we look at the next adjacent atom, so the next carbon, there's 2 hydrogens on that atom, and so it makes the hydroxyl hydrogen a triplet. When we look at the red hydrogens, we have 2 neighboring atoms, the carbon and the oxygen. There's a total of 3 hydrogens on those neighboring atoms. That would make it a quartet. The green hydrogens, we have a total of 5 adjacent hydrogens on the 2 nearby atoms, so that would make it a sextet, but we can just call it a multiplet, and you're not responsible for identifying them above a quartet. And then finally, the purple hydrogens, on the neighboring carbon, there's 2 hydrogens, so that makes it a triplet. 1,3-dichloropent-1-ene, they would be a doublet, a quartet, and a doublet. Now, when we look at the blue hydrogen, there's 1 neighboring hydrogen, so that makes it a doublet. The red hydrogen, we have 3 neighboring hydrogens, so a quartet, and the green ones, 1 neighboring hydrogen, so a doublet. Okay, so let's look at a sample spectrum. We have 1, 2, 3 different peaks. Okay, so we know that there must be 3 hydrogen environments since there's 3 peaks. The ratio of hydrogens in each environment is 3 to 2 to 3, and we get that from the integration trace that's provided for us. We know that the first 3 hydrogens, the blue hydrogens, are a singlet. The 2 hydrogens, the red ones, are a quartet, so there must be 3 neighboring hydrogens. And then the 3 hydrogens in the green environment are triplets. There must be 2 neighboring hydrogens. So those red and green hydrogens probably go together. That's probably an ethyl group, right? Because we have the 2 hydrogens, and then on the next carbon there'd be 3, and then those 3 hydrogens on the next neighboring carbon there'd be 2, if that makes sense. Okay, let's look at a sample problem. We have an unknown compound X with molecular formula C2H4O and it has the following IR and NMR spectra. So this is the IR spectrum, and this is the NMR. It looks really, really simple. And we also know that the mass spec shows peaks at mass to charge ratios of 15, 29, and 44. So we're going to use all this information in the data booklet to deduce the structure of X. Okay, so this looks like it's going to be really complicated, but we're going to break it down. And I'm going to sort of summarize this, but it will help if you have a copy of the guided notes or the PowerPoint slides so that you can refer back to the spectra as we talk about this. Okay, now when we look at the molecular formula, we know there's only one atom of oxygen and only 2 carbons. So this rules out ketones. We can't have a ketone if there's only 2 carbons. And it also rules out carboxylic acids because we only have 1 atom of oxygen. Okay? Next, we're going to look at the IR and deduce the functional groups present. So at 1700, we have a peak corresponding to a carbonyl group, which is likely an aldehyde. Okay? Because we know we can't have a ketone or a carboxylic acid. Okay, now, so in step 3, we have to examine the NMR. So a lot of times just counting the number of hydrogen environments and comparing to the number of peaks will identify the structure. There's 2 environments, one at a chemical shift to 2.2. So that indicates a hydrogen adjacent to a carbonyl. And then at 9.8, we have a hydrogen attached to a carbonyl carbon in an aldehyde. So that one's actually attached to the carbonyl. And in step 4, we're going to use the mass spec data to confirm what we think. There's a peak at 29, and that makes sense. That indicates that we would have an aldehyde. The peak at 15 is from the methyl group, which is the non-aldehyde carbon, so we have ethanol. Last thing you need to know is X-ray crystallography. This is a technique that uses reflected X-rays to identify bond lengths and angles in crystalline structures. You don't have to work with it. You just need to know what it is, that it exists, and what it could be used to do. Okay, that's it.